the channel. Today I want to talk about transfer learning, which is a method that can be used for performing tasks like image classification, and basically it is a technique where we use a solution from on domain and use it to solve a problem in another domain. So today I want to talk about AlexNet, which was proposed in 2012, and it was used for performing some large scale image classification task, and I will use it to classify CIFAR10 images in this video. Okay, so let's get started. So at first, import the required libraries. Sorry, typing mistake. Okay, so our PyTorch version is 2.0.00 and Torch Fusion version is 0.15.1. Okay, now let's define the device. Torch coder so device is device. Also check the total number of GPUs. Okay, so our GPU is this one, NVIDIA RTX A5000. CUDA device is CUDA, and total number of GPUs is 1. Okay, so let's apply transformation. Transforms.compose dot resize. For using AlexNet, we have to change the input shape to 224 by 224 pixels. Okay. Transforms dot normalize mean 0.45. and standard deviation 0.229, 24, 225. Okay, now let's see why we have selected these particular values and these particular values as well. Okay, so weights models dot AlexNet weights dot default get weights dot transform get. You can see this is the mean for our mean RGB values, RGB for the 3 channels in color images, and this is the standard deviation for RGB channels. That's why we selected these values. Okay, now let's load CIFAR10 dataset. So train datasets dot CIFAR10 root data src. So in this folder, in the current directory, so train true for train dataset, download true, and transform will be transform. So this one basically for this one. Now same for the test dataset as well. Okay, test dataset, this will be false. Okay, so our dataset is now being downloaded. Okay, so it has been downloaded. Now let's check the length. So length of the train dataset. Len train dataset. So for the test. So 50,000 samples in the train dataset and 10,000 samples in the test dataset. Let's also check the shape. Shape of the train dataset. So train dataset dot data dot shape. Same for the test as well. Okay, so let's run it. So we see 3 for color images RGB channels and 32 by 32 pixels for all the CIFAR10 images. Okay, train dataset dot classes. So we have 10 classes in this dataset. So airplane, automobile, bird, cat, deer, dog, frog, horse, sheep, and truck. These are the train classes. Okay, so let's copy and make a list. Organize properly. Okay, we can check the same for the test dataset as well. So see what are the same. Okay, so let's run it. And now visualize few images from the training samples. Okay. 5. Sorry. From the training samples. So 0 plt dot figure fig size 89 for image 1 in range 2448. Add subplot for 4 rows, 8 columns. This is the position. Now plt dot im show in data set dot data image 1. Sorry, image 1. Dot title classes train data set targets image 1. Font size will be 15. plt.x is off and we have to increment this for different positions. Sorry, typing mistake again. This is dataset. Okay, so these are the 32, I guess 24, not 32. So bird, frog, cat, dog, deer, airplane, cat, plenty of different types of images. Now let's do the same for the test case as well. Control C, Control V. So from the test samples, so let's change a few things. This will be two test 2. Okay, so these are few samples from the test. Okay, so we have different samples from that belong to 10 different classes. We have only shown 24 of them, so you can see dog, bird, automobile, etc, etc. Okay, now let's define the dataloaders. Okay, define dataloaders. Train dataloader. Dataloader will convert our dataset into an iterable. Train dataset batch size 32, shuffle true, drop last true. Copy and change. So this will be test and shuffle false. Okay. Length of the train dataloader. So len train dataloader. Same for the test. Okay, so 1562 for train dataloader, 312 for test dataloader, each with batch size 32. So since we have used drop plus 2, we have on less. If we didn't use this argument, then we would have had 1563 and 313. Okay, so now let's check the pre-trained network. Our case will be AlexNet architecture. So AlexNet models dot AlexNet pretrained true. Okay, so visualize the model. Pre-trained model architecture. So visualize. Okay, so let's create an instance. AlexNet send it to GPU, and torch info summary, pass the model, input size will be wedge size 3 because we have color, and we have already mentioned for AlexNet the input size will be 224 by 224. So this is our AlexNet architecture. So we have conf2d relu, maxful2d, conf2d relu, maxful2d, conf2d relu, conf2d relu, conf2d relu, maxful2d. Okay, then we have an adaptive average pooling. Then we have this is classification part. So dropout linear relu, dropout linear, then relu. 1000 because this was trained using ImageNet dataset, which has 1000 different classes. But we need to change it because in CIFAR10 we only have how many classes? 10 classes. So I need to change it. Also see model.parameters. So this is the feature extraction part, 12 layers, then adaptive average pooling, another layer, then in classifier section we have 6 layers. We basically need to change, we basically will change this part. This one we will use the already saved weights and biases. We will not train this part again. Okay, so now it's time to modified pretrained network. We will name it modified AlexNet architecture for CIFAR10 images. So let's modified AlexNet models.AlexNet pretrained true for param in dot parameters param dot requires grad false because we're using the pretrained weights and biases. Okay, but we need to modify these two part for CIFAR10. Currently this is suitable for ImageNet. So let's modify AlexNet. So at first dot avg pool. So nn dot adaptive pool 2d, output size 22. So instead of 66 we are changing it to 22. Then modified AlexNet dot classifier nn dot sequential. Now sequentially add classifier dot add module. So we have dropout at first. We want to keep this on same nn dot dropout. So p is equal to 0.5. Modified AlexNet, add module. Then we have a linear layer. Okay, so linear on. In feature. Sorry, nn dot linear in features on 1024. Out features 512. Modified relu. True. Now copy. This will be 2, 2, 2. So in this case, this will match previous output 512. We want to keep the out features same. Again, drop 3, 3. We do not need this one. This will match the previous output 512. And since we have 10 class, this will be 10. And we have added an extra layer. So we have dropout linear relu, dropout linear relu. After that, we have added an extra dropout layer. So instead of 6, now we have 7 layers in the classifier part. Okay. Modified pretrained. Okay, so now visualize modified pretrained model. So this is modified. Modified AlexNet. Architecture. Sorry. Architecture. So modified model. AlexNet, send it to GPU torch info summary. Modified model. Size 32, 3, 24, 24. Okay, we didn't do anything with this part, so this remains the same as before, but we have changed this one from 66 to 22. So previously we had 66 in ImageNet pool, now it is 22. And if we multiply 256 into 2 into 2 on 24, that's why we have 124 here. But for the original case with ImageNet, this one multiplication of these three results in this one. So we have changed this one to from 9216, we have made it on 24, then change this fonts as well. Okay. Model, sorry, modified model. So you can see we have changed these ones. Okay, now 10 define the train batch. Data labels model beyond model dot train send data to GPU, send the labels as well. Loss, three common lines, optimizer 0, loss backward, optimizer step, return loss. Now define the test batch. Batch torch test batch, data levels model and criterion, model eval. And return loss. And the accuracy function. Accuracy, data levels model. Grade levels output.max. So this thing gives grade values and the index of the maximum class. We only need the index for this case. Labels return correct CPU convert tensor to numpy, then further convert it to list. Now set up model to train. This will be modified AlexNet. criterion and optimizer. So criterion is also known as loss function. And optimizer. Okay, so model to train, modified AlexNet to the GPU NN dot cross entropy loss. Train the model. We'll train the model for 5 epochs. Create few empty lists. Train for epoch in range epochs. So n epochs. Okay. We'll call the train batch function and provide data labels, and model will be model to train. Criterion, optimizer, and append the par batch losses to this train losses list. TRN batch loss item accuracy function data labels model to train accuracies extent batch correct. Train par epoch loss np.array test losses, train losses, not test, mean. Train per epoch accuracy. Train accuracies. Okay, I have to repeat the same thing. Test. No need for optimizer. TST batch correct. Test per epoch loss. Test losses. Test accuracies. Hopefully everything is right. Test loss append. So train loss append. Train per epoch loss. Train accuracy. Same for the test. This will be test. Now print the model performance. Epoch plus 1 in epochs. Train loss. .4 Control C. This will be test loss. Train. Okay. Test loss, train accuracy. Test accuracy. Let's see if it works. Train accuracy is not defined. Oh, sorry. Train accuracy. I also made a mistake here. Okay. Let's see if it works or not. Thank goodness it's working. Okay, so the training is finally finished. So you can see the train loss gradually decreasing, test loss decreasing, then increased a little bit, train accuracy increasing, test accuracy is also increasing. So let's now plot model loss 15 and accuracy. PLT.figure fix size 16:4. Figure dot add subplot onto 1. PLT dot plot epochs train loss red line width 3, label will be train loss. Copy and change. Test loss, this will be test loss. PLT dot title loss curve, full number of epochs, y level will be losses, font size font size 20. So I think so. Now we have to just do the same for accuracy. So this will be 2. This will be accuracy. Accuracy. This will be accuracy curve. Accuracies. Okay, so this is a loss curve. This is the train loss, test loss much lower, and this is the accuracy, test train accuracy, red on. and green one is test accuracy. Finally 16, model prediction. Let's create two empty list. For A in, let's witness our model prediction for the first 10 samples in the test dataset. A model to train, retrieve our model from GPU to CPU, samples 0 and squeeze 0. Grade levels, output max minus 1. Labels dot append integer. This will give a tensor. We have to convert it to integer. Grade levels. PLD.subplots on 10. Fix size 15.5. For I in range 10, dot I am show dot permute on to 0. Set title classes samples I 1. Font size 20. Set color green. So this is our actual levels. Now I have to give a condition. If the actual levels are same as predicted levels, then set x label font size 20, set color blue. Correctly predicted labels, else just copy and set to red. This will be wrongly predicted labels. Set x ticks, set y ticks. Let's see if it works or not. No, it doesn't work. Oh, sorry, silly mistake. What happened? Oh, sorry, this is whitix. No, okay, we are getting some ugly lines here. Let's change it. Oh, finally. Okay, so this is our model prediction for the first 10 samples in the test dataset. So this is actual level cat, correctly predicted cat, sheep, 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 sheep. This is airplane but predicted as sheep. This is wrong prediction. Red color for wrong prediction. Frog, 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 automobile, automobile. This is frog but predicted as deer. Cat, cat, automobile, automobile. So for the first 10 samples, model gives 8 correct predictions and 2 wrong predictions, and probably it's makes sense. Accuracy is not that high, 81%, and it's also around 80%. Okay, this video has become very long, so that's it for this video. I have shown how we can classify CIFAR10 images by using pretrained AlexNet. This is transfer learning. We have changed the classifier part and made it suitable for CIFAR10. This is for ImageNet, but for CIFAR10 we have changed it to 10. And we basically, in transfer learning, we basically use state-of-the-art models to solve problem from another domain. So this model usually classified initially classified the ImageNet images, but since this is a state-of-the-art model, we can use it for classifying another types of images. For in this case, we used CIFAR10 images. So thank you for watching this video. If you like the video, subscribe to the channel please.